of inertia. So we have derived the equation for the rotational kinetic energy. The rotational kinetic energy, is given by half sigma mi ri square multiplied by omega square. Now we compared this formula with our standard equation of the kinetic energy. As we know that the kinetic energy of a particle or of a body which is in translation motion is half mv square. So half is there in the both of the equation. If we compare, half is there in both of the equation, and because it is a rotational motion, so instead of a linear velocity there is the angular velocity. Now here m is the mass in the translational kinetic energy. M is the mass, and mass is also known as the inertia. This is also known as inertia. So we can say that in the kinetic energy of a body in a translation motion is half mv square, where m is the inertia of the translation and v is the velocity, right? In the same way, in the rotational kinetic energy, there is the term of half sigma mi ri square omega square, where omega is the rotational angular velocity, and this term sigma mi ri square somewhere should be related to the inertia, right? This term sigma mi ri square should be somewhere related to the inertia. Right now this is a rotational motion, so let's call it as rotational inertia. Why I am calling this as inertia? The reason is because in the term of kinetic energy there is the mass, and mass is the inertia of the translation. In the same way, there should be the term of the rotational inertia in the rotational kinetic energy. So this term sigma mi ri square is the rotational inertia, and that's why we are defining this term known as the moment of inertia. What is moment of inertia? Moment of inertia is the inertia of rotation of a rigid body. I hope you are getting this, right? There is no doubt in this. Inertia of rotation, we are calling it as the moment of inertia. As the inertia of the translation, we are calling it as the mass. So we are defining it separately because we are getting this term by the similarity, by comparing the equation of the translation kinetic energy and rotational kinetic. We are getting this term. So nowhere you need to memorize that this is inertia. You can just conceptually understand it. Whenever you understand it conceptually, it will be very easy to keep it in the head, right? So let's write down. So for a rigid body or for a particle, let's say, or system of particle, let's draw it. Moment of inertia of system of particles I can say that let's assume that this is the axis of rotation and there are the particles situated somewhere like this. These are the particles. This is a system of particles where, let's say, this is particle 1, the mass of this particle 1 is m1, the perpendicular distance is r1. Let's assume that this is the particle 2, m2, the distance is r2, so on. And these particles are rotating with omega about it. So then the moment of inertia for this rotational motion is given as I equals to sigma mi ri square. Now what is mi? Mi is the mass of ith particle, and what is ri? Ri is the perpendicular distance from the axis of rotation from the axis of rotation. So this is moment of inertia for a system of particles. Now in this chapter we are going to deal with the rigid bodies. So somewhere we need to take the rigid body, which are the continuous mass distribution. So we need to define the formula for the continuous mass distribution. So we are going to apply this formula for the continuous mass distribution. Let's see how we are going to do that. So next, moment of inertia of continuous bodies. Or continuous bodies or the rigid bodies. Let's take it somewhere. This is the continuous body, right? I'm taking any random shape. It can be a ring, it can be a disc, it can be a sphere, cylinder, and anything, right? Right now I'm taking just any random shape. I'm just going to define the formula. I'm not going to calculate it, the final result for this shape. It will be very difficult to calculate for this shape. So that's why I'm just going to define how we are going to calculate it, not the final answer for this shape. Okay, let's assume that this is the axis of rotation. Now till this point, I think you understand, you are able to understand that what is the meaning of axis of rotation. Okay, axis of rotation. Okay, just wait a second. Yeah. So axis of rotation means the axis or the line about which the object is rotating, or the rigid body is doing the rotational motion. Now this is a continuous mass distribution. It means mass is distributed over the complete volume. Whatever the space it is occupying, the mass is distributed over that space. What is the difference between this and this? Can you think it? Yes, there is certainly some difference in that. In this case, which I have taken, I have called it as the system of particles. Whenever we say particle, I think you are able to understand what is the meaning of particle. Particle means something which is point mass. So it is a system of particles. It means there are multiple particles situated, not the mass distribution, right? So there is the mass in the space, but that mass is distributed in form of points, and these points are not continuous, they are discrete, and we are calling it as the system of particles. Whereas this is continuous body. It means it is a complete space of 3D, 2D or 1D space where mass is completely distributed. That mass distribution is continuous. Okay, so now we are going to calculate it. Okay, now again, just think it, this is a continuous body. How do we construct a continuous body? Yes, in the continuous body there will be small elemental masses or the point masses, isn't it? If I say that this is a continuous body, in the continuous body there are point masses or the particles which are combining and forming particles which are combining and forming the rigid body. So basically I can say a continuous body or a rigid body is the combination of the particles, but these particles are infinite particles, infinite number of particles, not some certain number of particles, right? Yes, so here there are infinite number of particles, but still in the continuous body I can consider is the combination of the particles, right? So I'm taking an elemental particle, and for this elemental particle let me define something. I'm taking this as elemental particle or infinitesimal particle. It means the size of this particle is approximately 0, right? For this elemental particle, I'm defining dm is mass of particle and r is perpendicular distance and from where? From you or from someone else? No, it's from the axis of rotation. So perpendicular distance from axis of rotation, right? Now just tell me, what is the moment of inertia of this particle? I'm just asking for this particle, this elemental mass. Just think it and give me the answer. You will say, okay, di is dm r square, or basically let's write it down, r square dm, right? Yes, so di is r square dm. This is the inertia of this elemental mass. Now there are infinite elemental masses in this rigid body, right? So now how to find out total moment of inertia? We are going to add it. So I, to find out the body of the body, is summation of di, right? And that is summation of r square dm. Now tell me, is it continuous mass distribution? Yes, of course, this is a rigid body. So can I replace this summation with the integration? If you remember the definition of the integration, what is the integration? Integration, where we use it? Basically, it is the summation only, right? But we will use it for the continuous summation, right? Okay, so I can say I is integration of r square dm. Of course, my handwriting may not be good, but I think you are able to understand what I want to convey, right? So yeah, just don't focus on my handwriting, just try to understand what I'm saying. So I is integration of r square dm. This is an important formula for the moment of inertia. Whenever there is continuous body, we are going to apply this formula. And there is this formula, I is equals to integration of summation of mi square. We are also going to apply this formula, but in which case? For the system of particles. There is a condition attached with that, and this is for any continuous body. Okay, so we have discussed something about the moment of inertia. Now let's move and let's discuss something more about the moment of inertia. Now we are going to know something more about the moment of inertia, on which all factors it will depend. Let's learn that. So factors on which, and I am going to call this moment of inertia as MOI. In the coming lectures as well, I will call it as MOI, so you can understand it, right? So factors on which MOI will depend. Okay, what is the formula for the moment of inertia? Integration of r square dm. So tell me, will it depend on the mass? Yes, of course it will depend on the mass. So it will depend on the mass of a rigid body, right? Okay, now next factor, I'm just going to take one example to explain it. Let's take example of a rod. This is a rod, right? Now I can find out the moment of inertia about a different axis of rotation. Let's first take the axis of rotation somewhere in the middle. Okay, and I'm taking the next case. Again the rod is there, but now the axis of rotation is somewhere on the end. Okay, just think it and tell me about which of the axis moment of inertia will be maximum, or will they be equal. So if you think about the formula is I equals to integration of r square dm, where r is the perpendicular distance. So if r will increase, then the I will increase, although the dm may be same, right? So from here we can understand about this axis, mass is distributed over the maximum distance. So I can say that for the second case, moment of inertia is same, greater compared to the first case, although the rigid body is same. I'm not changing the rigid body. So from here I can say that it will also depend on the axis of rotation. On the axis of rotation. Next, and again I'm going to take one more example just to explain it. Let's take this is a rod of mass m, length l, another rod of mass m but length 12. Tell me where the moment of inertia will be maximum. Axis of rotation is in the middle, the same axis of rotation. Tell me in which case moment of inertia will be greater. You can say naturally that the moment of inertia of 2 is greater than 1. What is the reason behind it? Because mass is distributed, the distance of the mass distribution is greater in the second case compared to the first case. So that's why you can say that moment of inertia is also dependent on the axis of rotation, it is also dependent on the mass distribution. Okay, let's know something more about the moment of inertia. Something more? Okay, yeah. So can you tell me moment of inertia, is it a scalar quantity or vector quantity? What is the formula? I equals to integration of r square dm. R square is a scalar and dm is also a scalar. So that's why moment of inertia is a scalar quantity. And can you tell me what will be the SI unit for this? SI unit. The SI unit will be, what is the formula again? The formula is I equals to integration of r square dm. So that is kilogram meter square.